Hello friends, in this video I am just going to explain to you the insertion process in an AVL search tree. The insertion process can be of many cases. We have dealt with one of the cases of insertion in one of our previous videos where we have done the insertion process where we were required to perform an LL rotation, which is a necessary operation which needed to be performed in that situation. But in this insertion, which I am going to explain it to you in this video, I am going to insert in a way so as to apply the RR rotation in order to make you understand, or in order to let you understand what is basically the RR rotation or the right rotation. It is basically a single rotation where we can perform only a single step of rotation in order to balance the tree in a way so that the tree, so that the AVL search tree after the insertion, if it loses the property of being an AVL tree, it can be restored to the AVL tree, or it can retain the properties of the AVL search tree. So, we are going to take an example and show it to you by means of an example or an illustration in order to show you how the insertion process takes place, which warrants an RR rotation to be performed on the AVL search tree after the insertion process. So, let's get started with the example and let me explain to you how the process takes place. So, let me take an example AVL search tree. Suppose I am going to take an example like this. So, I am going to perform insertion process once again in this video, insertion. So, this can be an AVL search tree. It has some nodes having some values in it, 34, 26, 44, 40, 56. So, this is an AVL search tree. Let us examine whether the balance factors of all the nodes in this AVL search tree conforms to the permissible values of the balance factors which are permitted in the AVL search tree. So, let me calculate those balance factor and show it to you. So the balance factor of this node is definitely 0 because it has no left subtree and the right subtree. So, the height of the left subtree and the right subtree are both 0. So, 0 minus 0 will give you a balance factor of 0. Same case goes with here also, that is 0. Here 1 minus 1 gives you a balance factor of 0 as well. Here 0 minus 0 gives you 0, and here 1 is the height of the left subtree and 2 is the height of the right subtree. So, that gives you a balance factor of 1 minus 2, that is minus 1 for this node containing the value 34. So, we can clearly see that it is an AVL search tree because it is a binary search tree. It looks like a binary search tree, and it is a binary search tree in fact, and it has all the balance factors which lie in the permissible values for the binary search tree to become an AVL search tree, that is minus 1, 0 and plus 1. So, this is an AVL search tree, and we are now going to insert a new node into this AVL search tree, and let us see what happens after that. So, let us insert a node like this. Suppose we are going to insert 65. So, we will insert this 65 where, because we have to compare this 65 with the root node 34. It is greater than the root node value. We will come to the right subtree 44. It is greater than 65 is greater than 44. We will go to the right subtree of 44 once again, and then compare this 56 with 65 and see that 65 is bigger than 56 as well. So, we have to insert the 65 node containing the value 65 on the right subtree of 56 like this. We will just link this 56 with this 65 and I will draw the AVL search tree after the insertion of 65 on this side. So, let me write this once again: 34, 26, 44, 40, 56. Those were originally there, existent in the example, in the question, and after the insertion of 65, the AVL tree looks like this. 65 will be inserted in this position. So, now we have, our task is to calculate the balance factors of the node after the insertion process has been done for all the nodes yet again. So the balance factor of this comes to be 0. The balance factor of this leaf node is also 0. This leaf node has a balance factor of 0. All the leaf nodes should have a balance factor of 0 because they have no child. They have no children. That is, the left subtree and right subtree of all the leaf nodes are empty. So for all the leaf nodes, we are giving the balance factor of 0. Now let me see the balance factor of this 56. That is 0 minus 1, that is minus 1. This is 1 minus 2 means minus 1. 1 minus 2 means minus 1. And let me say this one. This is 1. Left subtree height of 34 is 1. And right subtree height is 1, 2, 3. So 1 minus 3 means minus 2. So we see that the balance factor of this node, of this root node of this AVL search tree has become minus 2, and that minus 2 is definitely not in the permissible range of values for the balance factors for an AVL search tree. So now we will just do the backtracking procedure. That is, we will start from the newly inserted node, and in our way towards the root node we will just examine the balance factors of the different nodes and see where we first encountered the balance factor which violates the balance factor, permissible balance factor of an AVL search tree. So let me start from here. The balance factor is 0 over here. It is well and good. This balance factor is minus 1. It is also well and good. This balance factor is 44, has a balance factor of minus 1. This is also well and good. And after that, we go to this root node and see that the balance factor is minus 2, which is not well and good. Rather, it is just violating the permissible balance factor of an AVL tree. That is, minus 2 is not a perfect balance factor for a tree to become for a binary search tree to become an AVL search tree. So this minus 2 for this node, we will take this node to be A and see and examine that where this newly inserted node is present. The newly inserted node is present on the right subtree of the right subtree of node A. See this? The right subtree of node A starts from the value 44, starts from the node containing the value 44 rather, and after that we see that this 65 has been inserted in the right portion, in the right subtree portion of the node containing the value 44. So the newly inserted node is inserted, the new node is inserted on the right subtree of the right subtree of node A. So this will warrants a situation, this warrants an operation to be performed which is called the right rotation, because the newly inserted node is on the right subtree of the right subtree of the node A. So it requires me to perform the RR rotation, which is a single rotation. In that rotation we will just pull this 44, the node containing 44 from the right hand side to make it the root node, and the changes will follow after that. This 44 will be pulled in an anti-clockwise manner, and we will perform the RR rotation in that manner. So let me perform the RR rotation and show it to you how it is performed. So perform the RR rotation. We will take this 44, we will pull this 44 in an anti-clockwise direction so that 44 becomes the root. So I will write the 44 over as the root node. Now 34 will be moving towards left of 44, that is 34. 34 has the left child as 26. It will remain as it is connected to 34 in this situation. 44 has a right subtree containing 56 as its immediate child, that is 56. 56 has a right child in 65, and there is an interesting case here as well, that is 40 is on the left subtree of 44, but we have accommodated 34 in as the left child of 44, but where to put this 40? So 40 will be since the 40 was left child of 44 in this situation, 40 should be somewhere on the left subtree of 44. So to cater for 40 or to accommodate 40, we have to place this 40 over here. That is, 40 will be coming over here. So 34 has a right child in 40 now. So 40 now comes on the left subtree of 44. So this is the situation after the RR rotation has been performed, and let's check the balance factor after this operation has been performed. So the balance factor of leaf node, of all the leaf nodes will be 0 as explained earlier. So this is 0, this is 0, this is 0 as well. So the balance factor of 56 is 0 minus 1 means minus 1. The balance factor of this one is 1 minus 1, that is 0. The balance factor of this one is 2 minus 2, that is 0. So we can see easily that all the balance factors of this AVL search tree after the right rotation or the RR rotation has been performed lie within the permissible range of the values of the balance factors for an AVL search tree. So this AVL search tree is a perfect AVL search tree where the properties of the AVL search tree has been retained, and we have restored the properties of the AVL search tree after following this RR rotation. So this is the procedure of the entire RR rotation procedure needed for cases like this one after insertion of 65 in this example. So if you have any doubts and queries pertaining to this entire explanation of this insertion procedure, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.